Super excited for her talk today. So Twila is the deputy lead scientist at the National Snow and Ice Data Center, or NSIDC, and that's part of the University of Colorado Boulder's Cooperative Institute for Research in Environmental Sciences, which is a world leader in earth science, and a very long name. After she completed her bachelor's degree at Stanford and her master's and PhD at the University of Washington, she conducted research at University of Colorado, University of Oregon, and University of Bristol in UK before she returned to NSIDC in 2017. Twila is an expert in glaciers and ice sheets and the connections among ice, climate, ocean, and the ecosystem. And her primary focus is in Greenland and the Arctic. She's also a very accomplished science communicator. She leads a lot of efforts to improve the knowledge exchange between scientists and stakeholders, policymakers. So I'm very excited for her talk today. It's going to be really great. And without further ado, I'll pass it over to Twila.
Thanks, Sophie. Appreciate it. And it's been fun to meet with a few people this morning and look forward to seeing a couple of people after seminar 2. Feel free, if you have any clarifying questions during it, feel free to put them in the chat. And I think Sophia or Constantino will poke at me. But otherwise, maybe we'll leave the questions till the end. And admittedly, any bad seminar speaker, I have a couple extra slides that hopefully will make it through and will be useful to everybody. So let me share my screen here, get things rolling. Great. So I wanted to talk with everyone today about kind of mostly some recent work around the edge of the Greenland ice sheet. This isn't work that actually I'm doing currently at the moment. So we did some published work and I would love to see more of this happen. And maybe some of you will be intrigued and want to kind of take up some continuation of it too. So thinking about really the transformation of the Greenland ice sheet and how we're observing it, what we're observing, and some of those implications of what is really proven to be a total reconfiguration of the Greenland ice sheet margin. Along that, will also talk about a few other things. And so I couldn't list all of my collaborators here. But plus fantastic collaborators who you'll hear about throughout, and really none of this work is possible without them. That includes people writing papers with, but also proposals, having fun conversations, and basically keeping our community alive and well too. So before we get to Greenland, I think we have to orient ourselves to Earth's ice, where we are in it. Here, everything in blue, Earth's kind of glaciers and ice caps. Antarctica being our icy continent in the south, and Greenland, our ice sheet in the north. But every time I look at this map, I feel like we're sort of missing some sense of the real scale of the ice that we have here, because we're only looking in map view. But if we were to kind of think about how much ice is there, I'll show you in a couple slides, like starting to think about kind of how thick this ice is and what a difference that makes. But if we first start thinking about the changes that are happening on this global scale, where we're losing ice and what implications that has, we see that glaciers and ice caps, all of those areas in blue, and then the Greenland ice sheet are really our primary sea level rise contributors right now. And honestly, depending on the person you ask and the day that you ask them, they're going to say Greenland ice sheet or glaciers and ice caps are the #1 contributor right now. I don't think it has to be a competition. Suffice to say that glaciers and ice caps have been losing ice. You can get a real sense here for a longer period of time, but Greenland ice sheet loss over the last couple of decades has seen an incredible acceleration, and we've lost ice every year now since 1998 for the Greenland ice sheet. So that as we look at this map again, we can kind of think about where that loss is happening, but also think about that loss into the future, right? Our potential loss. And this is where the thickness of the Greenland ice sheet, which is about, reaches more than a couple kilometers in the interior. So about 30 Statues of Liberty from ground to torch, if you were just drilling down into the center of the Greenland ice sheet. And this is what really gives us that like true power of having, you know, global icy water towers containing frozen water on land. And because of the size of ice on Earth, we all end up talking about changes in these icy landscapes in which we have to bring up measurements that none of us would ever use in normal life, one of them being the gigaton. This is a nice graphic that Alex Gardner made that has 3 gigaton blocks sitting here in Manhattan. And so 1 gigaton being 1 billion tons or 400,000 Olympic swimming pools. So this is just 3 gigatons sitting here. And so you can appreciate now, as I transfer to this next slide, and we're going to look at ice loss around Greenland, you can appreciate the translation of these gigatons into kind of real quantities of liquid water. I think it's really instructive to look at these patterns of loss in Greenland. These are measurements made by the GRACE satellite and GRACE follow-on satellite, which are measuring gravity anomalies. If you're not familiar with this satellite system, I suggest Googling it. How it works is so cool. These 2 satellites are essentially talking to each other about their sensitivities to changes in Earth's gravity. And it gives us a really nice total mass loss. So I'm going to play this again, and we can just look at kind of our accumulated areas of mass loss. We have our summer gain, those ups and downs we're seeing on the plot on the right. But on the left, we have these nice arrows that can really give you a sense of the motion of the Greenland ice sheet. And how, you know, that intrinsic quality of a glacier, that it is moving, and also demonstrate that ice loss that expands across the south and the west, but really over this period of time reaches far up into the north, so that really all of our coastal regions of the Greenland ice sheet have seen significant mass loss. And that is kind of this environmental transformation that we're going to look at and talk about more. If we update this, you can see this was data coming from GRACE up into late 2016. If we update that with our last couple of years using GRACE follow-on data, you can see that our patterns continue. So we had some very significant ice loss in 2010. We then broke that record with ice loss in 2012, and actually 2019 met or broke that record again. As we think about where all of this is going, I think most commonly we think about and talk about these far field implications of change. So in Greenland, you know, counterintuitively, sea level is going to be lowering. It's all of us far away from Greenland that are feeling these effects as far as coastal erosion, saltwater inundation of freshwater resources, influences on sewage and water systems for coastal areas, you know, blue sky flooding, that occurs along the East Coast, kind of worsening of any number of coastal impacts. But over the course of this, I'll talk more about not just kind of thinking about the impacts of this transformation far afield, but thinking about the impacts of this transformation in Greenland too. So what are these sources of ice loss from Greenland? Well, we have ice loss as we get surface melt. We usually kind of think about this as surface melt changes and then ice loss that's coming from losing, you know, icebergs into the ocean. And these have commonly been fairly equal in kind of previous Greenland ice sheet in reasonable balance. But that balance has changed in more recent years, and the balance between kind of surface melt and iceberg loss has also been more variable. But as we look at our different processes, thinking about surface melt, we can start to recognize some of the really amplifying positive feedback loops that we have at play in Greenland. One of them, of course, being surface darkening. You can see really nicely in this Landsat satellite image the difference between having a very bright interior dry snow zone with a high albedo and high reflectivity, so that we're reflecting good bit of solar energy back out to space, versus the dark surface that we get here in our bare ice zone, and it's including these surface melt lakes that form. And we've recognize that the hydrologic and biologic processes darken the ice, algae, changes in grain size, things like that. But I think that we can also say, and research has shown this at this point, that it's simply snow line migration and bare ice exposure that is the much more kind of powerful process of exposing low albedo surfaces. So we don't have to kind of let the time pass for these other hydrologic or biologic changes to happen. Simply removing our snow is doing the vast majority of heavy lifting as far as being able to create a surface that's low albedo and encourages additional melt. This is especially concerning given that we have some other amplifying loops here in the Greenland system. When we think about surface elevation and area exposure to increasing temperatures. So this is a surface elevation profile that heads across this D section up here, but it's fairly representative. And you can really start to appreciate that, you know, if we have a 1 degree warming, say that is going to produce, I don't know, these are totally made up numbers, but a 500 meter elevation difference in what is exposed to temperatures that can cause melt. And you can appreciate that if we're here at the ice edge and we're going from, say, 500 to 1,000 meters in that elevation change, there's just not a lot of additional ice edge or ice sheet surface that we're going to expose. So we're going to expose something, but it's going to be fairly small area wise, which looks very different as we move into the ice sheet, where as we're jumping from 1,000 to 1,500 meters or 1,500 to 2,000, we start to get a more and more shallow ice sheet surface. And so our same warming is really going to expose a much larger area to melt. So these things, of course, playing together, because as we just established, we just have to uncover that ice to create a very strong effect for melting. And unfortunately, as our warming increases and as that snow line migrates towards the interior, much smaller changes in temperature can create much larger areas of exposed bare ice. The other process that we have in place is this ice loss from ice dynamics. All of this is over, you're kind of looking at the edge, and then, you know, off over the horizon is the interior of the ice sheet. And many of these glaciers being grounded, so we're not seeing the vast majority of ice under the ocean surface there. But this kind of process of moving solid ice happens all around the ice sheet. So everywhere here on this right-hand map, you're seeing kind of faster velocities and really watching these glaciers act as these conveyor belts, bringing ice to the ocean. This is an animation of some velocities from one of these glaciers here in the southeast region. They do have a seasonal signal and seasonal changes in their velocity, but you can really appreciate that there is kind of a constant flow, and then they really speed up and just, like, you know, squeezing your toothpaste tube and dropping all of this solid ice into the ocean. This is what that map looks like as far as where we're losing solid ice. And you can get a sense that we have some glaciers that are doing, a particularly effective job of moving ice from the interior. But we really do see this solid ice discharge all around the edge of the ice sheet too. And just to orient you, this kind of magenta color is icebergs and bergy bits in this melange that forms close to the Greenland coast and has been an area of a lot of interesting research as we understand kind of the material properties of ice melange, how it behaves, how it might influence the dynamics of glaciers seasonally or over the long term, and also how as we understand the role that it plays in these fjord ecosystems. But we also have kind of an amplifying loop that plays in here, in which we're thinking about this glacier in connection with the ocean, grounded on the topography beneath it. And we have some initial retreat or thinning that happens that pushes it towards a decrease in resistive stresses. We're accelerating the ice. It's essentially kind of like pulling it apart more, like pulling apart. In my head, I always get the image of those machines that are at the candy store that are pulling apart taffy. And this is then increasing our vulnerability to fracture. We get increased calving, which of course makes this glacier less stable, increased retreat. So this is one of these kinds of another vicious cycle that we think about, both as we're getting kind of thinning happening from the surface, warm ocean waters eating away at the base, things like this that are creating more of these positive feedback loops. But can we kind of, depend on these, and how do we see these as indicators around the ice sheet? So we know that we're losing ice all around the edge. We know that we've seen surface lowering. We know that we've seen kind of retreat of glacier ends. And often we connect this retreat with speed up, just in that loop that I just described, where we're retreating, we're speeding up the glacier, and we're retreating more. So if we just look at kind of how those patterns go together, this is some work where we brought together data about glacier velocities and glacier terminus positions from all of these glaciers you see here on the map on the right, and looked at how those were changing between the late 80s and the 2010-2015 period. And yes, many of these glaciers, the terminus is retreating and our velocity is speeding up. But we have a lot of glaciers that is simply not true. And this isn't a surprise, I think, to any folks who are paying attention to glaciology. But I think it's easy for us to still kind of fall into this problem of describing an intrinsic connection between glacier retreat and speed up, and kind of pointing to glacier speed up as these indicators of reconfiguration of the ice sheet. And I don't think that we should do that too much, because we do understand the sources of this heterogeneity. We understand that topography is such an important control on ice dynamics. And you can have a glacier retreat, but if it's retreating into a topography where the topography underneath it is higher than it was before, you're going to get slowing. It's kind of that process of moving a glacier into a more grounded state rather than a less grounded state. So I think we have a pretty good sense of this, and we understand, why it is that terminus retreat in these different areas is producing these different velocity responses. So if we can't kind of point to these velocity responses as maybe our best indicators of these transformations around the ice sheet edge, what can we point to? What are some good markers of rapid reconfiguration? And for this, we really have the benefit of technological advances in order to help us. So I'm going to continue talking about this data that spans the 1980s into the 2010s. And across this data set, we're using data that comes from the USGS Landsat suite. And there's a lot of development that happened across these suite of satellites that really kind of functionally gave our most recent satellite, it's like upgrading your glasses prescription. We have our radiometric resolutions improved. So we're just much better at now seeing details on the surface and kind of especially distinguishing surface, being able to see surfaces where earlier on we might not be able to kind of distinguish some of the details because you're looking at a very bright surface everywhere. But technology has advanced a lot. I want to point out, certainly Landsat 8 that's up now is just one of many kind of incredible satellite advances that we've made. And when I was starting to do work in glaciology, we didn't have any satellites that were kind of specifically looking at the ice sheets. You Landsat, you get images there, but that wasn't the main point. And that was true across a swath of satellites. And so we ended up kind of pulling stuff from here and pulling stuff from here and pulling stuff from there. Now, today, we have quite a swath of satellites that are specifically looking at the cryosphere and doing much more than just giving us optical image, also giving us information about, elevation change, topography, texture, regular views of places that matter to us on a variety of ways that we couldn't previously imagine looking at them. So now with our new glasses on, we can see changes, especially, so this is like a Nunatak area. And here, and we can especially see changes that happen here in the shear margins in ways that we never could before. It's earlier work, it was pretty hard to see very slow moving areas. It was hard to see slowing happen. And it was also hard for us to kind of distinguish things at the ice edge because of shadows, because of running into really high slope angles at fjord edges, these sorts of things. But now we can kind of move past some of that and see these details on a local scale. And there are definitely markers of reconfiguration that we see happen at areas all around the ice sheet. So I'm just going to show you an example of each of these. One is narrowing fast flow zones. This is Rink Glacier here on the West Coast. And for each of these three things, I'm going to show you image here of our velocity changes between this late 80s period and the 2010s period. Look at what the bed elevation looks like underneath this glacier from bed machine, and kind of a velocity of just what does sort of average speed look like on this ice. And you can appreciate here, we haven't seen significant change in this terminus, but nonetheless, we've seen some other changes in elevation, and we see this kind of edge ice slowing and this interior ice speeding up. And we see this kind of narrowing of fast flow zones happen in glaciers at locations all around the ice sheet. Some of them are kind of, long glaciers like this that travel through kind of longer topographically bounded fjord landscapes before they reach the ocean. But we also see this pattern happen on glaciers that are kind of much more embedded into the ice sheet. They aren't kind of these long flowing glaciers before they reach the ocean. They seem to sort of they seem, I should say, to kind of appear out of the ice sheet a little bit more quickly. I don't know if that's quite the right descriptor word, but I think you know what I mean. Another thing is ice flow rerouting, which is also, I mean, all of these are kind of simple to imagine because as we think about the ice sheet edge lowering, right? And the forces at play, we simply can't necessarily move ice in the same ways we could before. And so we see examples of rerouting our ice so that we have more ice flow coming over into this section than we do over into this section. Some of our remote sensing data is more usable for looking very closely at the vectors of velocity change and thinking about the directions of velocity change. But I would say that's an area where we still have improvements to make. And I think we'll continue to see more progress on that. Some of the ways that we process, for example, INSAR data right now does not make it great for looking at any kind of directional change in velocities. The way that we process optical is a bit better for that. And then another thing is glacier outlet abandonment, where I think we're going to see more and more instances of having places where previously we had kind of an active ice outlet, and those are going to go away. We're going to see, you know, places moving from being marine terminating towards being land terminating. And just given, I think, how rapidly we've seen changes over the last couple of decades, I think we may be surprised at how quickly some of these transformations continue to happen into the future. So what's some of the implications for seeing this coastal transformation? I wanted to show you this example. So Bea Chato, she's one of the co-authors on this work. We worked together and we extended that work for a poster that she had at AGU this fall, because we have not only did we kind of bring together the velocity and the terminus data in a Greenland-wide way, but we also looked at a little focus area in the Northwest, bringing in ice sheet surface elevation change data. And that is really interesting. I think helps us understand some of these potential implications of this transformation on a local scale. So these are some images from looking at another area that was not in that paper, combining velocity, terminus, and elevation change data. So here you can see kind of images in the velocity changes that have happened in this region. And we compare those with surface elevation changes with kind of an early period of lowering in both of these outlets, a bit of thickening in this outlet, and then moving in towards this 2008 to 2014, where these outlets start to become very distinct from each other. As far as their patterns there, we lose our thickening happening up in the more northern section of this outlet. But if we then take this information and look at where it implies our subglacial hydrologic networks might be, because remember, we have water moving underneath a large portion of the Greenland ice sheet, some of it being frozen to the bed, but the vast majority, and certainly here around the periphery, having liquid water at that interface between ice and topography. We can look at this difference here. So these are calculated hydrologic network channels. So I can't tell you for sure that there's water moving in these ways, but I think it's really powerful to see this transition from having, for example, a hydrologic basin here that's outputting subglacial discharge into this more northerly fjord that continued here around the turn of the 21st century. But here, once we're into the more recent decades, we seem to have lost our ability to really push water out into this fjord. It's getting rerouted here out into this more southerly fjord. And this is where we have to start to wonder about what kind of implications this is going to have for our fjord environments. So we know subglacial discharge drives warm fjord water circulation. This graphic giving us a sense of summer where we have these subglacial discharge plumes entering into the fjord, being an active part of this fjord system, bringing nutrients, bringing sediment, bringing water that is fresh and cold into this environment. And we have a sense that these fjord environments are used by a wide variety of living things, right? Polar bears, whales, fish. Greenland has a very active hunting and fishing economy. Certainly kind of marine harvest and exports is one of the major parts of their economy. So they're very much, people in Greenland are very much thinking about, the health of fish, the health of ecosystems, where are living things moving, and what does that mean for where they can do hunting and fishing and what that's going to look like. And so we have some sense that all of these things are connected, but honestly, oh, sorry, my cat is arriving for seminar. But we still have questions about what that might mean. And I just wanted to give you one example of some fun research that others have done that maybe helped us to start thinking about what these implications of moving around our subglacial discharge in big ways, like moving it from one fjord to another, what that might mean. This is work that Mark Hopwood and others published, and I'll walk you through a few different examples here. So what you again have is our glacier outlet, our subglacial discharge, and they're pointing out the possibility that if you have here not a very thick glacier, kind of a more shallow fjord, as our subglacial discharge water, we know that it comes out, it's buoyant, and here it's going to entrain waters in this area that aren't nutrient rich. So this fjord just isn't deep enough to have kind of nutrient rich, deep water. And so our subglacial discharge comes out, it entrains this nutrient deficient water, moves it up into the photic zone, but it doesn't, who cares? We're moving up nutrient deficient water. So there's not any change to productivity in this kind of case. If we move to a fjord and glacier system where we have a bit more depth, now we're starting to get these warmer, more nutrient rich Atlantic waters at depth. And so as we're getting subglacial discharge, we're actually entraining nutrient rich water, and that water is able to reach the photic zone before it kind of achieves neutral buoyancy. And so we're moving these nutrient rich waters into the photic zone, potentially enhancing productivity. And if we move one step further and we have an even deeper fjord where we still manage this part of entraining the nutrient rich water, but we just can't maintain buoyancy for these subglacial discharge plumes all the way up to the photic zone. So we're just dropping this nutrient rich water off at some midpoint, and it's not getting to the surface, and so we aren't having any of this kind of increased, enhanced productivity. So I think there's still a lot of open space where we haven't connected all of these dots. We haven't connected kind of the wildlife and the fjord nutrients and kind of oceanographic physical behavior and the rapid reconfiguration in the ice sheet, but so many of these pieces are now kind of being explored, and we're able to explore them in details we haven't before. And that, I think, is really exciting and going to allow us to start doing more and more work that's really pertinent to the people here in Greenland. You know, what are the things they care about? What's their industry? This is a huge processing factory that they have in Ilulissat on the West Coast, where they're always getting in, you know, fishermen ships for processing and exporting. And you can see, I mean, this is just what feeds people there too, right? So we're beginning, I think glaciology, we've had a lot to catch up on in a short period of time. People have been doing incredible work, and it's always been a challenge to kind of like stretch our time and space scales in bigger and in smaller ways. And we're beginning to really be able to look into these longer term futures of the ice sheet. We've had such wonderful advances in understanding ice dynamics and being able to model that. And that's giving us really powerful information that I think, especially kind of bringing to policymakers, bringing to national and international bodies to inform their decision making, because we can, those are groups that are kind of looking at these representative concentration pathways scenarios and thinking in multi-hundred year scales as far as what that means for what we need to do internationally. And we can demonstrate to them what a difference human action is going to make in this long-term future of the ice sheet. So that's very powerful. But I think we're now also getting to a point where we understand that, I mean, we are past this point now where we understand, even if we are, you know, taking very strong global action here, this is what this, the model I was just showing you looks like here in a close zoomed in way under RCP 2.6, right? Talk about aspirational. And we can appreciate that even with this kind of very strong action, this incredible transformation of the Greenland ice sheet edge is going to continue. We're going to be opening up new fjord waters. We're going to be changing where ice flows in Greenland and how it moves. And that means we're going to be changing all of these other things about sediment and nutrients and water. But we are getting to the point where we have instruments that are helping us to be able to remotely observe on scales that we can maybe use for local and near-term prediction that is going to be so beneficial to people on the ground in Greenland, and kind of move not just towards understanding the ice sheet as a way to really grapple with sea level rise on a global scale and areas far away, but also ways we can understand the ice sheet and the environment that are going to be very helpful for people who are needing to transition within this rapid change happening there. So I'm very excited about this, and I think there's many pieces of the puzzle are being explored, but we still have a lot to do to fit them together. So that's kind of the main bit I wanted to chat about, but I am just briefly going to give you two kind of advertisements. This is your homework for anyone here who is Greenland curious. One, I'm lead a project that we're developing, Q Greenland. If anyone hasn't heard of Quantarctica, that's another thing you should explore. This is basically an open data, open platform GIS tool where we curate and bring together a lot of different data about Greenland all into one place. It's all been transformed for you, gathered for you, etc. And you can download the package and play with it. So it has everything from like kind of local detail you might need when you're planning travels to Greenland, but also really region-wide if you're wanting to make figures or kind of explore some of the different data that different disciplines have. So we're working towards having lots of disciplines represented so that people can start to make connections between kind of the space that you work in and the other things that are happening around Greenland on a scientific research wise, and also using it for education. So next week on February 24th, where we have version 1.0 is released. And so anyone who's Greenland curious, love it if you check it out, download it, use it, sign up for our newsletter, and send us ideas about data improvements. We certainly are, we have a small team working on this, and there's lots of expertise out there that we don't capture. And so I'd love to hear from people's experience. We'll have at least a couple more years of development on this tool. So we would love to hear from people. And my one other bit of Greenland homework for anyone on this is people are maybe familiar with the Greenland Ice Sheet Ocean Science Network. We have entered a new phase. I've learned a lot in this project about kind of the long time scales sometimes required for building communities and creating science discoveries, but this project now has a 5-year funding for connecting networks of researchers internationally who are working on the Greenland ice ocean margin. That includes the ice, ocean, ecosystems, communities. And we have a form right now just to express interest, start making and building some community connections, and we'll have summer schools and workshops and some working group projects and things like that. And I would love anyone interested in Greenland's margins from any kind of perspective or discipline to go there and fill out that form and at least keep your ear to the ground, if not become more involved. So, all right, I'm done.
All right, if anyone has questions, you can use the raise hand function or just go ahead and unmute yourself, I suppose. Duncan Young.
Hi, Twila. Great talk. I guess these effects that you're seeing, the rerouting, the abandonment, the narrowing, by themselves, they would tend to reduce flux. It's almost like the ice sheet is trying to fight back against its demise. Do they actually represent negative feedbacks in the system, or?
I think that really probably have to dig into that more at this point. I think that probably looking at some of the rates of change, and we're maybe just getting to a point too where, because that elevation change information is so important to that, and that's been a bit more limiting factor than the velocity and terminus data part, but that is starting to improve. But we haven't introduced combining the elevation change and the velocity and terminus positions on a more ice sheet wide scale. That's some of the work I would love to see happen. I'm hoping that maybe we can find a way to continue some more of it at the University of Buffalo with that group there. But really, I'd be excited. Anyone who wants to jump up and down. But I think that introducing that is going to help us to maybe get a real better picture of whether it's the kind of how much it's going to kind of help essentially kind of keep ice in place.
So, thank you.
Ella, I have a
Hi,
question. I'm wondering what you see as like the next thing that we need to kind of target as a community, given like you kind of like with the Q Greenland, given that you've seen like now all the data that might be available for researchers, like what do you see moving forward that we need to kind of tackle?
I guess you might not be surprised to hear this answer from me, but I do think it's making these connection points. That remains very difficult because different disciplines have different conversations. So like one of the projects I'm working on right now, we're trying to understand the Southeast glacial sea ice environment so that we can help make insights about polar bear behavior. And this is requiring us to try to characterize the coastal environment at spatial scales that are very difficult, especially if we want, like that kind of time scale. And so making these connections across disciplines, it's funny because in some ways doing this work, I feel like, I think I was originally probably supposed to write like a glaciology paper with this. And I'm like, well, I don't know that I'm telling glaciologists anything new, but we're having to characterize the environment in ways that I wouldn't do that if I was just working on glaciological research. And that's this part of connecting disciplines that I think is really difficult, is sometimes it forces you to do things in ways that don't feel like disciplinarily super productive, but it's required to make this connection space. And so I think it's making these connections, and it's also filling in this like 10 to 50 year time scale of what will be happening. And that is so difficult given the uncertainties we still have of topography and ice thickness and things like that. But I think that's what the will be required for us to start to connect to the living environment.
I thought the one of the most interesting parts of your talk was when you were talking about the Hopwood paper about the different fjord productivity you get, and that's something I hadn't even crossed my mind. So if you're thinking about the question that Ginny just asked, like, is it more important to understand what's happening right now with the fjord productivity, and then looking forward to like if Greenland retreats within the next couple tens of years, what the fjord productivity is going to look like? Is that sort of like a really big open question? This is something I've never really thought about, is the actual productivity within the fjord and how changing that margin might actually change how much productivity you get in fishing, I suppose. So is the big question there just like, what actually are the types of productivity we have now? Like, do we not even know that? Or is that more important to predict what they're going to look like in the future?
Well, admittedly, this is a question where like invite in the biologist over here to give us some ideas. But at least what I've noticed, like in the bits that I've been able to learn, in the conversations I've been able to have, which I want to say, like small fraction, I think there's still a lot of kind of connecting, what is the most important thing for a species being in a place? Is it water temperature? Is it some kind of nutrient something? Like I kind of think that there are a lot of those sort of ecosystem connections are still difficult to make. And maybe in many instances, the kind of monitoring is how we answer those questions now, in the sense of like, these have been observed here, now they've been observed here. Can we connect it with some, kind of hindsight of what environmental changes happen, and can those connections be made? My sense is that there's still enough question marks, like even that Hopwood et al. Kind of work, we had been thinking about whether we could use something like that to try to like classify Southeast fjord systems and say something about the productivity there, but that we still have like pretty big uncertainties in some of the bathymetry and like what are those where is that water mass? What is that depth? And so this is where I feel like you have to have people, you have to have like an oceanographer at the table, a glaciologist at the table, you know, fish scientists at this table, like, and that's really, really challenging. So I guess I don't have a better answer, because I think it's pretty unclear still. And not to say that kind of all these disciplinary advances don't need to still be happening, you know, I mean, people are learning things on all of these fronts, and decisions are being made on the ground in Greenland, you know, X, Y, or Z, or based on observations. But I know in my case, getting started working with someone whose full focus was biology, we had several years of casual conversation before we endeavor to do things. And it still sometimes feels like grappling around in the dark to figure out how to do it and feel like we're making, we're able to come to solid conclusions. I don't know if that really answered your question.
Yeah, it was a very broad question. Yeah, it seems like a lot, like we have a lot of the data that we want, but like a big point that I got from your talk is like maybe the resolution just isn't there yet for certain types of problems that we have. I think that's really interesting.
Yeah, and I think it's, I mean, I definitely notice, I think some of the challenges that we face, I mean, so much work is being done to help. We have much more data coming in than we did in decades past. But it's also so much that it can be, you know, like the kind of work that you lead in, thinking, how do we combine data sets? How do we work towards maybe automating items, things like that? But I think there are still a lot of questions. Like we had endeavored to first use radar backscatter data for characterizing some of these fjord things, but some of the assumptions we had about what radar backscatter data would tell us didn't turn out to be true. And so we've gone back to optical data for trying to say some things about the fjord surface conditions. But of course, optical data is a problem with clouds. It's a problem with polar night. And so you're sort of back at a more limited time scale again, versus you know, radar data. So I think there's still a lot of back and forth. There's still a lot of places where answering our questions do require kind of that people hours trained monkey activities. I guess I'd be curious too, maybe Sophie or Ginny, or just how you think you guys get to see, yeah, machine learning, great, I like that too, is kind of, you see a different perspective and group than I do, and I'd be curious kind of how it feels from your end on being able to connect some of these dots in new ways that we couldn't before.
It's Alexei Portnov. I have a question, if I may, or even probably two questions. Thanks for the talk, Will. It was really interesting. So my first question is about those meltwater plumes. And you've mentioned, of course, they're buoyant. So basically, that's obviously due to the density difference between salt and fresh water. Is temperature at all a factor there? So because the meltwater plumes can be, they're close to the melting point, right, to freezing temperature, and the ocean water it can be much warmer. So how do they fight each other, this density and temperature difference? So basically the question is, are those meltwater plumes always upwelling, or it's site specific? And because it can differently affect the productivity in different fjords.
I can't think of having heard of any examples where your subglacial discharge doesn't have some buoyancy, although I think that that can, depending on the ocean water conditions, you can reach neutral buoyancy quite quickly, and is often going to be, you know, associated with the different ocean stratification that you have in the fjord. I don't know, Patrick, I want to call on Patrick. I feel like you've maybe seen more data on this sort of thing than I have. He's maybe doing other things, and we can just look at it as a nice picture there in a fjord. But
I'll speak to that. I think that the subglacial discharge is being funneled through just a single or like maybe 2 or 3 channels. So it's a huge volume flux of water, number one, and then it's cold and fresh water. So it's almost always buoyant in the fjord. The water at the bottom of the fjord is very salty. That's why it's at the bottom. So the heat is trapped at the bottom just because of the salt content. And so it's you're injecting this very different type of water into the fjord. So it's just forcing it to become buoyant and entrain at the terminus phase, which causes melting at the terminus phase.
But I can't think of any example. I mean, I can think of things where people have, you know, instances where it's reaching neutral buoyancy very quickly because of the stratification in the fjord, and that kind of like not very deep, but I think it would be very rare.
Glaciers like exiting the terminus or exiting the fjord, and then it's just dumping into the surface. But anywhere that it's like exiting the terminus, you know, anywhere below 300 meters where the Atlantic water is situated in these fjords,
you just have to have really thin glaciers.
Yeah.
To see anything different. Yeah.
Thank you. And my second short question. So those models you showed for different RCP scenarios and Greenland thawing, I did not notice there any sea level rise in neither of those. Why is that? Or is it just like even the model for 8.5, which 1,000 years from now, the shoreline was exactly the same as presently?
Maybe it was just seen incorrectly. Here, let's go back and look at this.
Or maybe it's just not that significant, so you cannot see those couple of meters difference, but it just looked similar. Well, thank you anyway.
Yeah, because I think you're, oops, let me go back here. Is this what you're asking about?
Yes, this thing.
Yeah, so there is significant sea level. So this is the sea level contribution, just from Greenland. And I think here are you asking about this kind of very early period time?
No, I'm asking about like if you notice, if you try to follow the right-hand picture, the shoreline doesn't seem to be changing at all. It's kind of stable.
Oh, yeah. Kind of where is it that you're losing ice?
Yeah, so we don't see the shoreline retreat. Yeah. Mm-hmm.
Yeah. So that's related to largely kind of where the climatology, so to speak, the where you're gaining ice. So this southeast coast is where you get your highest precipitation rates in Greenland. And so kind of it's commonly, sorry, I got to move this around. This actually, when it ends, it gives you kind of a nice sense of where remnant ice is expected to be around Greenland, having to do with where you get precipitation, what the topography underneath the ice sheet looks like. So that's why it forms kind of this interesting pattern of retreat, where you kind of end up with ice sticking around more on the eastern side than it does on the western side. But you don't have, we see glacier retreat in these areas. And I think if we were to zoom in, and actually this at the end of this might, it's a little hard to see. You do, even in this RCP 2.6, you do expose land in these areas along the eastern coast. It's a little hard to see, and it's certainly not as dramatic as in the western coast.
Yeah, thanks. I guess what I meant is the eustatic level, sea level. So you need to, I think you expect to see the shoreline shrinking and Greenland becoming smaller. That's the case for like small islands.
One of the problems with sea level estimates is that they don't really account for a migrating shoreline. They're simply just like adding water to the top and not thinking about the boundaries so much. We talked about this in a seminar recently, which is how I know about it.
Okay.
And so I think that that's like something that we might need to think about, as there's been, like as Twila is showing, there's just so much reconfiguration to the coastline happening, and that has its own consequences. So, you know, how does that moving boundary influence everything?
Right.
Yeah, thanks for jumping in, Ginny. I had not understood your question properly.
Yeah, I'm sorry. I should have asked it clearly.
No, no problem.
Charles looks like he has a question, but is being shy.
Actually, I was going to jump in with the whole sea level thing. I'm using my iPad instead of my computer, and it was messing me up. But I think the whole coupling between sea level, you know, isostatic adjustment and ice sheet. I mean, ice sheet models have a hard time with it. Climate models have a hard time with it. It's like there's this kind of interface, kind of with that boundary moving around, is supremely difficult from a numerical point of view to kind of keep track of that. I mean, the challenges are just profound, so if you're, you know, if you're a scientist out there, it's actually pretty exciting, right? These challenges. So it's an opportunity to think about that. But yeah, the animation lacked any change of sea level but actually probably the ice sheet model did include some. It doesn't involve ice-ocean interactions, but it was probably just a graphics thing. Because even our graphics, the way to even present this stuff in animations, you have to update the data sets. And you know, it's like, even if the model does, it doesn't mean your animations do. So it's a fun problem.
Yeah, in this case, also the sea level is fighting against the isostatic rebound, so it may be more or less like, not that large. Yeah, I understand this thing. Yeah.
Yeah.
And then, of course, going to look different at different places on the Greenland coast, too. So there's those kinds of changes too. And then I think there was just a paper not too long ago. They were kind of looking at the difference that it made to keep your ice mask properly updated. And what a huge difference that can make in the results, you know? And I mean, just that you say, like, computationally so difficult, and observationally, we're not quite there yet either. Although probably, Ginny.
We're gonna make time evolving ice masks.
Yes, I was gonna say, I feel like maybe you might be thinking about that.
Yeah, and we're also gonna get elevations with Bea from the ASTER data.
Yeah. So forward progress, but it is a lot of things to try to include to attempt to give people better numbers.
So we need more people, more money.
All right, well, it's 11:35, so thank you, Twila, for such an engaging talk. Yeah, she'll be back in May, I believe, for a Gen Science Policy talk if you're interested in her work on that. But yeah, as Twila says, we all have a lot of work to do on Greenland, so let's go. Thanks, Twila.
Thanks for attending. It's really a pleasure to see everyone.